Let's dive into vector databases, which is a term you may have heard recently and thought, what is a vector database? Why do I need a vector database? And I'm going to talk about what they are first. I'm also going to dive into how I've used them in the past. In fact, why don't I just do that to start with? I've used vector databases that I've written from scratch, in fact, when I was building a social media network where we were able to use that vector relationship to recommend different users on the platform. So that's really the core concept is you want to find a way to find similar things and then recommend them. So to start with, let's go ahead and define the key terms. Vector embedding. This is actually a little simpler than you think. It's a numerical array. So think of a Python list where it represents an entity's features in n-dimensional space where the proximity equals similarity. Probably the intuition here to think about would be a three-dimensional relationship where you have x and y and z. If you plot a three-dimensional relationship, you can see if you rotate that relationship, you can find things that are similar to each other. So that's essentially k-means clustering, right? If you plot a k-means cluster, the XYZ, you'll say, oh, okay, here, this is what's actually happening is that, in fact, these relationships are because of this factor, this factor, this factor. For example, I've done some relationships with k-means where I was clustering, and I found that real estate would go up in certain areas because of zip codes, or I would find with sports potentially the reason that people are spending more money for a team is actually real estate itself is one of the key factors. Or you could find nutritional quantities of carbohydrates, fat, and protein. Like there's lots of different things you can do with three-dimensional space. So it's kind of the similar intuition with vector embeddings is that you're looking at a numerical array, and in this in-dimensional space, it could be more than three dimensions. It could be four or five, etc. It could be 1,000 dimensions. You're going to figure out which things are similar. Now, there is a little bit of a problem if you get into too many features, that you get this problem of the curse of dimensionality where everything is close to everything because there's so many dimensions. But the intuition there is that it's a way of finding similar patterns. In terms of a vector database, this is a specialized database that's optimized for storing and retrieving vectors based on similarity rather than exact matching. The intuition again here is that if you had products, like if one customer bought 10 products, another customer bought 9 products, and you compared that 9 out of the 9 were the same, then it's very likely that that customer would want to buy that 10th product, right? That's the intuition. Likewise with following people on a social network. Now, in terms of similarity search, this is finding items with vectors that are closest to a query vector. This would be a distance metric. We also have cosine similarity. This is the measure of angle between vectors. The values would range from -1, which would be opposite, to 1, which would be identical. Another key term is nearest neighbor search. This would be algorithmic problem of finding the closest vectors to a query vector. And then we have AN, which is approximate nearest neighbor. This is a algorithm that would trade perfect accuracy for dramatically faster search speeds. So that's the definition, the context. Let's get into the 5 whys now, which is a technique that I like to use to get to the root of a problem. So why do you need a vector database? Very good question. Well, traditional databases can't find similar items. A relational database is really good at an exact match. For example, where category equals shoes, but it can't efficiently answer what's similar to this product. There's a vector similarity, though, which enables this fuzzy matching because it's a numerical fuzzy matching, right? Again, if it's a similarity and your 9 out of the 10 items are the same, you have a match, right? 90% correlation between those two arrays. Likewise, in the next step would be, why do modern machine learning systems represent things as vectors? And this is where we get into language models uh, and they encode semantics in the vector space. So again, we know that things are similar, etc. And so this is where you start to divide things into this vector space. And then the product relationships would exist in this high dimensional feature space. And then the mathematical operations on those vectors will then reveal hidden relationships. So again, the intuition here is very similar with k-means clustering, but it's just expanded to very complex high dimensional features. Okay, let's look at the why number 3, which is computation costs are exploding at scale. So if you're going to do computation across millions of different products, very computationally expensive to do that, because think about this, you would have to figure out every single relationship, and this could easily get into an unoptimized factorial runtime. But with specialized indexing structures, they can reduce the complexity from O to the N to O to the log N. And also vector databases will optimize these operations specifically. So a vector database is designed for these kinds of multidimensional relationships and finding similarity. Now let's look at the next why, which is better recommendations drive business metrics. So if you look at some of the larger companies that are using this, some research shows that e-commerce can attribute maybe a third of the revenue to a recommendation engine. So if you're giving people the recommendations on the things that they're interested in, this is a key way to drive additional sales. Likewise with, let's say, Netflix, something like 75% of viewing comes from recommendations. So if people are finding the things that they want, this is one of the positive drivers of recommendation. Now, there are some negatives, and especially with thought bubbles, and people get into a feedback loop where they get potentially more and more recommendations. That's the negative part of it. But the positive part of it would be that they could drive better business metrics. Now, in terms of 5, this continuous learning would create a compounding advantage. So every time a customer would interact with a recommendation model, the vector-based system would adapt without doing complete retraining, right? Because it's just a database that finds similarities, and these advantages compound over time. So really, in a nutshell, let's think through how the vector similarity works. In terms of the mathematical foundation, it would be products, content, users, whatever it is represented as in-dimensional vectors. So, for example, a book vector could include maybe science fiction, romance, historical, and then the machine learning would determine these dimensions automatically. And then in terms of computing the similarity, most commonly people use cosine similarity. So it's a dot product of normalized vectors. This would be very fast computation as well. And then it's very intuitive as well, right? Again, if you said 9 out of the 10 items are the same, 90% similarity. In terms of the theory to practice, the best way to think about this is content-based recommendations would be similar to what you're viewing now, and it's purely based on item feature vectors, and it works with zero history. And this is a big problem with recommendation engines, is if you have a cold start, like you have no data, how would you know what to actually recommend to somebody? We also have collaborative filtering via vectors. So users like you also enjoyed this, right? This is a good way to have user preference vectors derived from interaction history, and then item vectors derived from which users interact with them. And then a hybrid approach would be combining the content and collaborative signals, maybe like an item vector plus recency weighting plus popularity bias. So this could mixture together these approaches based on how much data you have. So if you're starting a new system and there's no data, then maybe you need to start with popularity, and you combine that until you get more data, and then you start blending more towards, let's say, the content-based recommendations. In terms of implementation, there's a few things to think about in terms of, scaling considerations. Do you want to do in memory versus disk? And then also, what are the libraries you want to use? One of the ones that I think is an emerging best practice is this quadrant Rust-based library. which I found to be pretty good. And if you're already using Rust, it works very well with your existing CLIs or your web application. So really to close up here, the key intuition here is that pretty straightforward now with vector databases to get started. And it's a way of really finding similarity between things. It's a unified approach to content and collaborative signals. And then there's some strategic advantage that comes from the data, not just the algorithms, because the data itself is going to allow you to give recommendations. So that's really the essence of why people are using vector databases. And it's worth investigating, in my opinion, the Rust ecosystem combined with Quadrant.